Hi everybody, my name is Jerry Chen. I'm a senior research scientist from Vanguard. I'm working on the research team at the Center for Analytics and Insights. So today we will have a discussion about using deep learning to model tabular data. So I'll talk to you about a system that we have developed for propensity optimization in the scope of marketing. So the agenda today is to first talk about the motivation for our solution, and then briefly mention how deep learning can help unstructured versus structured data sets. And then we will dive into a detailed methodology called TabNet, which we utilized as the backbone of our propensity optimization system. And lastly, we will look at some results and analysis from the model output. So to first motivate this project, let's introduce the idea of propensity modeling. This is meant to forecast a target population's likelihood of performing a certain action in the future. For example, in the marketing context, those actions that we're looking for can be accepting a personalized offer or making a purchase or signing up for a particular service. These propensity models can often be siloed, and they don't consider a client's propensity to, for example, adopt other services or products. So as users of these models, marketing managers are often unaware of other marketing efforts our clients are suitable for. Which means the same client can receive multiple offerings at the same time to nudge their behaviors. So this can lead to a fractured and unpleasant client experience, which is against our values at Vanguard. So to mitigate these confusions, we sought to model propensity for our clients that can incorporate multiple business lines at the same time. So this way, our marketers will have a more holistic view of a client's propensity to adopt different products and services, which where like better decisions can be made on which populations should be targeted for which lines of business, with an increased awareness of other business lines in the scope. In addition, we also produce uncertainty values, which avoids point estimation that are common in isolated propensity models. And this gives us a sense of how reliable the produced scores are. And the propensity optimization system is built for these kind of purposes, especially to forecast propensity and estimate uncertainty for 3 specific business lines. I cannot disclose the actual name, but let's just call it Service 1, Service 2, and Product 3. Our objective is to empower always-on marketing, where marketers have this kind of improved vision on a regular basis so that we can continuously monitor the propensity for adoption and be prepared to market at any point in time. So as opposed to figuring out the population that we want to target after we come up with a marketing campaign. So now I kind of want to switch gears and compare and contrast structured versus unstructured data sets. So this is important to keep in mind because the data sets that we deal with in the financial setting are often structured. So the ones that we leverage for this particular use case is also structured data. And unstructured data on the left side, those are qualitative data like text, images, videos, or audios, and etc. They're stored as specific files that correspond to their format. They typically need more storage space than structured data and are hard to analyze without AI tools, especially deep learning. On the other hand, we have structured data. So these are quantitative or categorical features displayed as numbers, dates, values, and strings. For example, like this puppy data set on the right side. The records are stored in tabular format with rows and columns. And often we use relational databases like SQL to process these data. They often require less storage space and they are easier to analyze with more simple tools like Excel. So over the recent years, we have seen deep learning being leveraged to process the unstructured data type very well. Neural networks are pushing the envelope on what is possible in all of these domains. So the question here is that can deep learning also help structure data? And this is also another of our motivations to find out the answer to this question. And the short answer to it is yes, there are many studies showing how neural networks can be also very effective on structured data. And I'll show you how one of them called TabNet is leveraged in our work. So for structured data sets, we're probably quite familiar with shallow or non-deep learning methods. They have kind of become the method of choice by many practitioners on data science platforms like Kaggle. So these methods use the idea of boosting, which means to combine a set of weak learners to form an ensemble by kind of sequentially adding predictors or trees to correct for the errors of its predecessors. So there are several variants of these decision tree-based methods, which all have great performances on tabular data sets. And going to the deep learning part, so generally deep learning methods on structured data, they can be categorized into three different groups. First, we have differentiable trees, which are actually motivated by the strong performance of decision tree-based ensembles like XGBoost that we just mentioned. Decision trees are not differentiable and they do not allow for end-to-end optimization. So these methods, they modify the decision functions to be smooth in the internal nodes to make overall tree function and routing differentiable. And secondly, we have attention-based methods, which is inspired by the success of attention-based architectures for different domains. So most prominently, this is the transformer model from the NLP field. They apply attention-like modules for tabular deep learning. And then lastly, there are also some other approaches to improve multiplicative interaction and then incorporate feature products in neural networks. And the method that we will be focusing on today is TabNet, Attentive Interpretable Tabular Learning. So this is a work published in AAI 2021 by Eric and Weister from Google. So this is an attention-based method, as we mentioned before. So this chart from the paper is kind of like a high-level view of the TabNet architecture. So we can see that TabNet uses multiple decision steps to select different combination of features to produce the output in the next step. It kind of draws inspiration from decision trees as well, where feature selection in each step is kind of the key to obtain decision boundaries. And the outputs from all the steps are aggregated together at the end for the final prediction. So on a high level, there are several advantages to use this model. So we can first have end-to-end learning with raw input data. We can understand feature importance on the instance level using attention. And then there are also encouraging results on many tabular dataset benchmarks. It also offers a form of interpretability and experiments with the unsupervised learning setting, which we have not yet leveraged in our work yet. So this is a more detailed look at the TabNet architecture. We'll also be double-clicking on the two transformers that's in this pipeline in the following slides. So globally, the input features, they go through iterative steps after an initial batch norm. And then each step will do the same thing, much like a recurrent neural network. So the number of steps is a hyperparameter that we predetermine. So what does each of these steps actually do? So the input goes into a subcomponent called a feature transformer. And then it's split into two parts as shown in the step 1. The attentive transformer takes one of these splits in each step to create a mask, which becomes the input of the feature transformer in the next step. So these masks also contain information on how to select features in each step. And all the output ReLU activations from each step are actually added together for the last fully connected layer. So, and since this is a deep learning architecture, we can customize the output based on our task, whether it's binary or multiple target, whether it's classification or regression task. So looking under the hood of the feature transformer, we can see that it's a neural network with different components that we may be already familiar with. So we have the blue fully connected layer, and the green batch norm. And then we also have the red GLU activation function, which is the gated linear unit. So this is just the component-wise product of two linear transformations of the input, and one of which is sigmoid activated. And then these three components make up what is called the GLU block in this chart. So in the feature transformer, we have two of these GLU blocks that are shared across all the iterative steps. And two of them, they are dependent on each decision step. We also have skip connections going across different blocks as well. So the overall architecture is actually more like a residual network than a standard transformer. So as we mentioned previously, the output is split into dimension D and dimension A. They become inputs for another ReLU activation for the next step, and then the attention transformer respectively. And then this is the attentive transformer. So it's there to select which features on a high level to kind of utilize, utilize in order to produce the final output. And I think this may be the important part to understand why TabNet works well on tabular data. So we have this prior scale here, which are weights applied on the input dimensions to give information from the previous step. And then initially they are all equal to 1, but in the next learning step, the prior evolves and it becomes a product of masks from previous steps. This means past information is merged for selecting features in the current step. And I will also have a lambda hyperparameter to select how flexible it should be to select a feature across multiple decision steps. In addition, we also have a relaxation hyperparameter here. That's basically the lambda that I talked about. And then there's also a sparse max function to construct this mask in the network, which are the feature weights. And then sparse max is a sparse version of softmax. And it basically enforces a lot of the dimensionality to be 0 in order to select features in this particular decision step. So with all of the details in mind, overall, you can just think of it as a very dynamic reweighting process to select the relevant features in each step that are dependent on the previous learning steps through the usage of prior scales and also masks. So in summary, the more steps you stack, the bigger the model will become. And then each step trains a specific mask to select the features, which contribute equally to the final layer. And then ultimately, masks can be averaged to get instance-wise interpretation for the model's output. And a feature has been that has been masked a lot, basically has low importance for the model. So for our use case particularly, we are framing our problem as multiple target binary classification task, as we want the system to produce a propensity score for each of the 3 business lines by learning on the same data set altogether, rather than creating separate models. So we changed TabNet's output dimensionality and then used 3 sigmoid layers at the end of the network as our multitask objective, which are not mutually exclusive to each other. And then on top of this flexibility, TabNet also offers inductive bias for structured data, as well as the scalability on large, high-dimensional data sets. Therefore, it became the model of choice for us. So for our model, let's first take a look at an example output from our system. So the first column here is basically the client number, and then the 3 columns that are after that is basically the propensity score for each of the 3 business lines. And then we also have uncertainty on the very right side. So we process our scores through ranked percentile transformation. So we'll get into that later, but this means that the lower the score, the higher a client ranks in propensity to adopt one of these services and products. And we also produce uncertainty values for each business lines, respectively as well, on the right. And then the lower the uncertainty, the more confident we are about the prediction for that line. In terms of data source, we use internal data source with product features to train our model. And for labels, since our data set is a snapshot at a specific timestamp, we look at conversions in the next 6 months without any attrition in a week for each service. The rest will be our kind of negative sample without any positive labels. And after we create these labels, we randomly take 20% of the data as held out test set, leaving the rest as training data. Because of there is some imbalance in the data set as well, there's also a need for uncertainty estimation. We actually create an deep ensemble of 10 TabNet models that are trained on individual smaller subset of the original training data. And each of these training set has the same positively labeled points from any of the business lines. And then we also randomly sample the same number of negative points so that each training set is balanced. More on the deep ensemble technique. This is a simple method to aggregate multiple versions of neural network models that are initialized differently in order to make more robust prediction and to produce uncertainty measures in our use case. So the authors for this paper, they show that ensembling neural networks can explore different regions of the loss landscape and then end up with different weights to capture multiple modes of the solution space, as illustrated by this graph, while Bayesian methods only explore the areas close to one mode rather than many modes. In our case, we trained 10 different TabNet models with the same architecture, but have variation both in the training data as well as the different random initializations to create this ensemble. Here's a scoring pipeline illustration for the system. As you can see in this flowchart, the input features, they are pushed through an ensemble of 9 models, actually, out of the 10 models that we trained. So this way we can omit the lowest performing model. And each model produces 3 outputs. And then we then merge them to create the final score and uncertainty. During ring inference, I also mentioned we transform the raw outputs to produce ranked percentile scores. For each model, we do this by first fitting the scores on the 20% test set into quantile cuts, and then saving these buckets created by these cuts. Then we transform the raw scores for the entire population into these buckets to produce the percentile ranking. For example, a score of 10 means the raw score ranks in the top 10% of the held out test population for one particular model. So the lower the score, the more likely a client may convert to that product or the service. And then the median among the 9 percentile scores are used as our final outputs. As I mentioned, we have 9 different models to create the ensemble. In addition to that, we also have the uncertainty of the scores that we produce, which are created by taking the difference between the second highest and the second lowest model to avoid outliers. We compare TabNet's performance with other standard methods, including logistic regression, random forest, and a simple 5-layer re-zero. This is basically a residual neural network. For each method, we train 10 different models with random initializations on each subset. And then we also use early stopping to report the average performance of raw scores on 10 validation sets. TabNet achieves the best ROC AUC performance across all the 3 business lines. We believe that this is because of TabNet's inductive bias on large-scale structured data set and its flexibility to implement multitask knowledge sharing. We noticed that a standard ResNet kind of neural network without any kind of inductive bias on structured tabular data set cannot really outperform simpler baselines like logistic regression or random forest that only allow for separate modeling. So when looking at our outputs, separating out specific populations that we're interested in can help us kind of see how the model performs for different subpopulations rather than mixing our outputs for various type of clients altogether. So here we want to show some comparisons of clients that are contacted versus not contacted via emails in the last 3 months. So in terms of score distributions, our system assigns higher propensity in general for the contacted clients and higher uncertainty values for the non-contacted split. And this pie chart represents the proportion of the splitted populations. We see that there is a gap in performance between the ROC AUC for the 2 split groups. So this actually stems from the fact that an email contact does not necessarily lead to a conversion. Thus, learned from historical data distribution, our system is not making as good of a prediction for the email contacted split. And then for product 3, the distribution looks a little bit different because this product can be actually purchased again rather than being a one-time adoption like Service 1 and Service 2. And then this suggests that our system assigns high scores to people who have been contacted, but the performance does not suggest that it's this kind of simple filtering is appropriate to identify true adoptions. In this figure, the set of splits is for different types of leads. So these are population that we have more confidence in eventually adopting our products or services. For example, we may have interacted with them on a deeper level. Again, we observed that across all of the 3 splits, that higher propensities and lower uncertainty are predicted for the blue lead group. And note that the ROC AUC gap between the 2 split groups is smaller compared to the previous slide, where we're showing the email contact split. So this suggests that historically there are more conversion signals occurring in clients from these lead groups, which validates the fact that qualifying for lead of any kind is a more concrete step towards conversions than being sent marketing emails in the past 3 months. And then we also look at our outputs to validate what it has kind of learned across different products and services, which is not possible with previous models that are isolated for one particular use case. So between the first 2 services, we see a negative correlation, which actually aligns with our business intuition that these 2 services when they're doing marketing, they are mutually exclusive from each other. And for service 1 and products 3, there's little to no obvious linear relationship. So the population is kind of scattered in many regions. And then finally, between service 2 and product 3, there appears to be a positive relationship, but it's less pronounced. We also examine the relationship between the scores and uncertainty for each service. There's a consistent concave distributional pattern across all 3 outputs. This means that we are more certain towards the extreme scores on both tails and less certain when we are in the mid-range. So this suggests a good opportunity for novel exploration in targeted marketing, where marketers can actually experiment with relatively higher ranked clients with relatively higher uncertainty, which are the population that are circled. So by focusing on this region of the client base, we can also supply more evidence to the model in the next iteration, given the adoption results from these experimental campaigns. And to further investigate the uncertainty values, we bucket our population into uncertainty bins, which is reflected on the x-axis. Note that the uncertainty greater than 50 is relatively high, so we group greater than 50 into its own range. And then recall is plotted on the y-axis when the uncertainty range is varied. We use recall because we care much more about missing a true conversion than making a wrong positive prediction. We can see a downward trend for recall rate within each uncertainty range. This shows that we perform better with population that we have less uncertainty of. But at the same time, this shows that not all conversions happen in the same uncertainty range. So it's important to experiment with less certain population as well when using the model to identify marketable populations. And this is the last slide. To understand how much additional adoption we can gain by iteratively increasing the target population, we show a conversion gain table to give details for every 10% increase in the top population size. So naturally, by increasing this number of clients in the top scored population group, the system captures more conversion counts in the test set. However, the gain here is diminishing in terms of additional conversions when each additional 10% population is added down the list. So we can see this downward trend in the percentage and the uplift columns. So notice that the last row includes all clients in the test population, which means the conversion percentage for this row is the average baseline adoption rate by random targeting. So we're highlighting the fact that by targeting the top 10% clients in propensity, the model can provide more than 5 times the conversion rate than random selection for each account type. So we believe this provides significant evidence on the effectiveness of this system in predicting future adoption for each service and product within an unseen test population. So that's the end of my presentation. Included some reference here, and then that's it.